Hello everyone. Now I shall teach you alternating series. The alternating series, very special class of series, very interesting, and they often appear when we study power series. When we study power series later, we will see many alternating series. Here you can see the general form of the alternating series. A sub n, this is the general term of the series, and the general term of the series is factored into one alternating factor, -1 power n minus 1. So when n changes 1, 2, 3, this alternating factor is +1, -1, +1, -1. It's called alternating factor. It also can be written like -1 power n or -1 power n plus 1. Doesn't make any difference. It goes plus minus plus minus. Together with the alternating factor, we have b sub n, which are positive terms. So the general term is a product of alternating factor and positive terms. Now for alternating series, we have a very special test. But before the test, I want to show you one example. Remember the harmonic series, which we studied before, this one here, 1 plus 1/2 plus 1/3 plus so on. This harmonic series divergent. Divergent by the integral test. Remember, when we extend 1 over n to 1 over x and integrate from 1 to infinity, we get a divergent logarithm. However, if we alternate these terms, if we consider the series -1 n minus 1 with 1n, which goes 1 minus 1/2 plus 1/3 minus 1/4 and so on, this series actually is convergent, and the limit of this series is natural log of 2. We shall see this later. But you can see how from one divergent series we can get convergent if we alternate the terms. I shall tell you now the alternating series test. Alternating series test. This will explain this phenomenon here, how the second series convergent when the first is divergent. Alternating series test, we shall abbreviate AST. Important test. So given an alternating series, I shall write this again. Remember, b sub n are positive numbers, positive sequence. If this sequence approaches 0, b sub n approaches 0 when n goes to infinity, and it approaches 0 decreasingly. So b1 greater or equal b2 greater or equal b3, decreasingly, bn plus 1 is less or equal b sub n for all n. Then the series is convergent. The series is convergent. So this test tells you about such convergence. So it's sufficient for the general term to approach 0 decreasingly, and you get convergence. I want to remind you that we have a divergence test, which says that if the general term does not approach 0, C is divergent. But if the general term approaches 0, this is not sufficient for convergence. Remember the harmonic series. And also pay attention that here B sub n is not the general term. The general term is the product with the alternating factor and B sub n. B sub n is the positive part of the general term. Okay, let's see some examples. Look at the series. Here on the top I shall write negative n plus 1 square root n plus 1 here, and goes from 0 to infinity. So we can distinguish here, we can write this, well, alternating factor like that, 1 over root n plus 1. So here we have the alternating factor, and these numbers here are B sub n, the positive part and general term. Let's write explicitly B sub n is 1 over root n plus 1. And this sequence approaches 0, and it approaches 0 decreasingly. The decreasing is very clear when n grows, the denominator gets bigger and bigger, and with each step you get something smaller, dividing by bigger denominators. So this is decreasingly going to 0. And the alternating series test says that series is convergent. Very simple example. Let's look at another one. Look at the series. Here is my alternating factor. Now it's just like that, starting from 1 to infinity. And then I have on top n squared, and below n squared plus n plus 1. Will I write negative 1 power n or n minus 1, n plus 1? Doesn't matter. You can just multiply the entire series by negative 1 and it doesn't change convergence. What about this one? Here B sub n, the positive factor is n squared plus n plus 1. We can easily determine the limit here. Divide top and bottom by n squared, and you can write this 1 over 1 plus 1/8 plus 1 over n squared. And this has limit, and the limit is 1 over 1 plus 0, which is 1. So the limit is not 0. And this series is divergent. It's divergent because the general term does not approach 0. The general term is all this thing here. A sub n does not approach 0 divergent by divergence test. Divergent series by divergence test. General term does not approach 0. Here the positive parts approach 1. With plus minus, it's not 0. A sub n is actually divergent. Another example. We look at the series. Again, alternating factor here. Root of n on top. And below we have 2n plus 3. And goes from 1 to infinity. So we look at the positive factors. B sub n here is root of n, 2n plus 3. Let's find the limit. I can divide top and bottom by n. It's one simple thing to do. Reduce. If you factor, let's do it this way. If you factor n from the denominator, you can write it n 2 plus 3 over n. And then n here you can write like square root of n squared. And this reducing by square root of n, it becomes 1 over root of n. And here 2 plus 3 over n. All this has a limit. 0 times 1/2, which is 0. So the general term approaches 0, and we can see that it approaches 0 decreasingly. So this checking I shall just skip. We can compare two consecutive terms, or you can just take the derivative. If you take the function root of x over 2x plus 3 and differentiate, you can see what is the sign of the derivative. The sign of the derivative should be negative to show that it's decreasing. We can use this theorem from calculus, from Calc 1. If the derivative on function is negative, the function is decreasing. So in many cases we can use this for sequences. Another example, another alternating series. Here alternating factor, arctangent n. Now B sub n is arctangent n. Let's write it like that. And when n grows to infinity, we know the limit of this. Mentioned this several times. The limit is pi over 2. Arctangent x grows to pi over 2 when x grows to infinity, and here n is a discrete sequence going to infinity. The limit is pi over 2, which is not 0, and this series is divergent. Now carefully, it's divergent not because of the alternating series test, it's divergent because of the divergence test. The general term does not approach 0. The general term here, a sub n, is negative 1 power n, arctangent n, and this does not approach 0. It's actually divergent. Okay, next example. Look at the series n cosine pi n over 2 power n. N goes from 1 to infinity. Well, is this an alternating series or not? Actually, it is an alternating series because cosine pi n is nothing else but negative 1 power n. When n is 1, cosine pi is negative 1. When n is 2, cosine 2 pi is 1. And like that, when n grows step by step, you have plus 1, minus 1, plus 1, minus 1. So we can write here this in the form negative 1 power n times n over 2 power n. And the positive factor b sub n is n over 2 power n, and we can find the limit of this this way by using L'Hopital. Limit b sub n, it extends to function of x over 2 power x when x goes to infinity. And we can use L'Hopital, take ratio of derivatives. This will be limit 1, derivative of x, derivative 2. X is 2x, natural log of 2. X grows to infinity. Natural log of 2 is a constant. 2 power x grows to infinity. 1 over infinity is 0. So again, we can apply the test. It's approaching 0 decreasingly. we're not checking this. Trust me, it decreases really. You can take the derivative and carefully verify this. So the series is convergent by alternating series test. Okay, I will stop now with applying the test. You'll see many more examples in the book, and please go to your homework and do all similar examples. I want to go to the last topic in this section, approximating the sum of the series by using one special estimate. Approximating the sum of the alternating series this is important. I want to underline it in red. So suppose we have a convergent alternating series. I shall call it S, the value of the series. And or n minus 1 doesn't matter. Let's say just negative 1 power n, b sub n, from 1 to infinity. Then we have such estimate. I shall write important estimate. S, the sum of the series, this is not a good S. S, the sum of the series minus nth partial sum is less or equal b n plus 1. So the n partial sum S of n will be when n is 1, it starts from negative b1 actually. Negative b1 plus b2 minus b3 and so on, plus negative 1 power n b sub n. This is the nth partial sum, and the difference between the nth partial sum and the value of the series is less or equal b n plus 1, term next after b sub n. It's a very important estimate. I'm not going to prove it here. You can see the proof in the book. And it doesn't really matter how you start at the beginning with n plus 1 or n minus 1. It's important to write nth partial sum correctly. So if you start with negative 1 power n minus 1, the first one will be positive. This doesn't change the estimate. It's an important estimate I want to put in a box. I'll put it in a green box. I like green color, like that. And I want to show you how this estimate can be used to approximate the value of the series. Here is one example. Suppose we have this series. S is sigma negative 1 power n 1 over 3 power n times n plus 1. And we're starting from 0, the summation, n equals 0 to infinity. Okay, b sub n here, 1 over 3 power n times n plus 1. Obviously it approaches 0, decreasing. With each step the denominator gets bigger and bigger, so getting something smaller and smaller. So the series is convergent. Alternating series test. And we have this estimate. S minus S sub n is less or equal b n plus 1. Now we had to write what is b n plus 1. Look, here is b sub n. In the place of n we had to put n plus 1. So this will be 1 over 3 power n plus 1 n plus 2. We have this estimate. And now, suppose I want to find the value of the series with some precision. I want S minus S sub n to be less than 1 over 100. So, because of our estimate, it is sufficient to take, because we have this estimate, sufficient to take b n plus 1, b sub n plus 1 to be less or equal to 1 over 100. Now we can solve this for b sub n. Replacing b sub n with its equal, this will be 1 over 3 n plus 1 times n plus 2. We want this to be less or equal to 1 over 100. So if this is true, the difference between Sn and S will be less than 100. How to solve this for n? Let's flip first. 3 n plus 1 times n plus 2 shall be greater or equal than 100. For what n this becomes true? Let's see. When n equals 1, we have 3 squared times 3. This will be 27, 3 cubed. That's not bigger than 100. Let's go to the next one. When n equals 2, we have 3 cubed times 4 now. This will be 27 times 4 will be 108, already greater than 100. So we can stop here. Just take S sub 2, partial sum with index 2. Then S minus S sub 2 in absolute value will be less than less equal than b 3. When n is, this will be 3 and this will be less than 1 over 100. We just compute what is b sub 3. Here it is. This is 1 over b sub 3 actually. 1 over b sub 3 is 108, so b sub 3 itself will be less than 1 over 100. And let's see what is S2. S2, reading the series. Let's look at the series again. We're starting from 0. So first S2 will be negative 1 power 0 b0 plus negative 1 first power b1 plus negative 1 squared b2. So this will, the very first one is when n equals 0, this is just 1. Then we have minus 1 over 3 times 2. And then plus 1 over 3 squared times 3. And this will be 1 minus 1 over 6 plus 1 over 27. We have common denominator 54. It's when you put it common denominator, we get the number 47 over 54. So this number, this is S2, let's write again. This number approximates the value of the entire series with error less than 1 over 100. S minus S2 in absolute value is less than 1 over 100. So you can continue like that. If you want to get better precision, you can take more terms of the series and get better and better approximation. Okay, I'll stop here with this example. You see other examples in the book. The alternating series can be approximated, the value of the series can be approximated by using this special estimate. And it's done often in mathematics in various situations when the series cannot be computed by any other methods. People just find approximate values this way. Okay, we're stopping here. Goodbye.